Hello everyone. Welcome to Learning at 11th hour. Please do subscribe to this channel if you like the video. So this video is going to be about a step ahead of what we saw in the previous video about how we can use multiplexers to implement logical functions. In the previous video, we saw how we can do it with just the multiplexers and no extra gates. So we can use, for example, if there is a function with four external inputs involved in it, we can use the 16 cross 1 mux where all the four external inputs act as the select lines, and we could connect all the minterms that are involved in the expression to plus 5 volts, so that when the select lines select those particular inputs, the outputs would be 1 and the remaining are grounded. If we did not have a 16 cross 1 mux, we could actually go ahead with implementation of the function using an 8 cross 1 mux. But this time we have to go for something called as the implementation table, where we identify how the inputs are and how we can use just three out of the four external inputs to act as select lines. And the fourth one will be involved in the input of the multiplexer. We could use different combination of select lines. It need not be fixed, and that's what we saw in this part of the video. Now today what we are going to do is we are going to go a step ahead and we are going to say that I don't have an 8 cross 1 mux, I have only a 4 cross 1 mux. And now I'm going to show you how, if we have a 4 cross 1 mux, how can we implement the very same function. So let's go into the video. So this was the problem that we were looking at. This is the function we want to implement using the 4 cross 1 multiplexer. So when we talk about a 4 cross 1 mux, this is how it should look. 4 inputs and 1 output mux. So it will have I0, I1, I2 and I3. So 2 to the power number of select lines is equal to 4. So therefore the number of select lines should be equal to 2, because 2 power 2 is 4. So since this is the inputs and X is the select lines. So now we can say that we have two select lines for this, S1 and S0, and one output. So this is how it should look. Now we have four external inputs coming in to implement this function, out of which we can choose any two to act as our select lines. Say our select lines is C and D. So now A and B are going to be involved in framing the I0, I1, I2 and I3. C and D are going to act as my select lines. Now what is the different combinations of A and B that are going to be used, so that when the select lines C and D uh, assume different values 0, 0, 0, 1, 1, 0 and 1, 1, these particular minterms will throw out a value of 1 at the output of the multiplexer. We need to find this out. So again, we are going to go for something called as the implementation table, like we saw in the previous example. In this implementation table, it's going to be slightly different. It's going to be like a grid. In this case, a 4 cross 4 grid. So I'm going to choose the AB to be along the vertical uh, alignment and CD in the horizontal. Now, this is looking very similar to a K-map, but this particular grid is not a K-map. So we need not write the 0001 in the gray code representation. So let it be continuous 1011. And CD could also assume the values 0001, 10 and 11. When CD is 00, because CD are the select lines as mentioned here, when CD is 00, I0 will be selected. When CD is 01, I1 will be selected. When it is 10, it is going to be I2. And for 11, it is going to be I3. Now, we are going to see where our ones are going to be placed. So, the minterm 0000 is available. Minterm 0001, 0001 is available. And so on, you can actually number it. So this is continuous only 1, 2, 3, 4, 5, 6, 7, 8, and so on. Since this is not a gray code representation, we are really not looking in for adjacent cells here. So this would be 3, 4, 5, 6, 7. This is 8, 9, and the last box should be 15. So these are the minterms for which this function holds good. So this is the first step. What we've done is we've framed a grid. We've used the select lines and aligned it horizontally. And A, B are the input of this function, which is involved in framing the I0, I1, I2, and I3. Now we need to find out the expressions for I0, I1, I2, and I3. So in order to do that, we have to see what are the different combinations of A and B for which I0 is 1. Similarly, for what different combinations of A and B is I1 holding good? Again, same thing is applicable for I2 and I3. In that case, we are going to need a very small K map because this is just going to be a 2 cross 2. So let's see the expression for I0 in terms of A and B. So we form a small grid here, and we are going to mark 0 and 1 here, just as we do in K-map. Since this is just a 2 cross 2, this is already in the gray code representation. Now let's observe I0. I0 is 1 for AB 0, 0. So when AB is 0, 0, which is this box, I0 is going to be 1. For AB 0, 1 and 1, 0 also, I0 is 1. So AB is 0, 1 and 1, 0. So this is the K-map for I0 in terms of A and B. Now if we perform the grouping, we'll be able to find out the expression. So let's group this. So this is going to be my first group. These two are together, and the expression for this is A dash. These two are adjacent to each other. The expression for this is B dash. So when we put this together, we get I0 is actually A dash or with B dash. Or using De Morgan's, we can say this is A dot B, the whole bar, right? So that is the expression for I0. In a similar manner, we are going to find out the expression for I1. So let's again frame the grid to find out I1 in terms of A and B. So here again, we have a 2 cross 2 grid where A and B are available. Now, observing this column of I1, we see that I1 is 1 for AB is 0, 0, and it is 1 for AB is 1, 0. For 0, 0, it is 1. For 1, 0 also, it is 1. Now, in order to find out this expression, we'll have to group it, and this group is nothing but B dash. So we can say that I1 is equal to B dash. When we look at I2, I2 is not connected to either A or B because we see that there are no midterms over here. So all of them are actually 0, so to say, which means I2 is going to be grounded. So we can say that I2 is equal to 0 always. Okay. Now let's look at I3. Now in order to find out I3, again, we are going to frame the grid. So I3 in terms of A and B, we get this small grid, which is 2 cross 2. And from this K map, we are going to mark the midterms. So AB00, I3 is 1. AB is 1, 1, I3 is 1. So let's mark it. For 0, 0, we get a 1. For 1, 1, we get a 1. Now, if you look at this, this is nothing but an odd function kind of a representation. So therefore, we can say simply that this is A dash B dash plus AB. So that is X nor between A and B. So that is A X nor of B. So if you see, we've got the expression for all the 4 inputs to the multiplexer, I0, I1, I2 and I3. So let's now draw the multiplexer such that it implements this particular function. So we have a 4 cross 1 MUX. We know that the select lines are C and D. We know that it's implementing the function f, and it's got four inputs. So let's first draw a and b. These are the two input lines, right? That is running across. From this, we can tap whatever wires we want. So I naught is nothing but a dot b, the whole bar, which is NAND. Okay. So let me take a and b and draw a NAND gate. So here I get a dot b, the whole bar. This is the first input. Next I have I2. I2, sorry, I1 is B dash and I2 is grounded. So if I just connect a NOT gate over here and join it, this is going to be I1. I2 is just grounded. I3 on the other hand is, as we saw, A XNOR of B. So if I have A here and B here, I draw an XNOR gate, XOR with a bubble, and connect it to my third input of the multiplexer, right? So 0, 1, 2, 3. So these are the four inputs. So this connection with C and D as the select lines and A and B, with extra gates, the NAND gate, the XOR gate, the NOT gate, connected to the 4 cross 1 MUX will implement this particular function where f of A, B, C, D is going to be summation of 0, 1, 3, 4, 8, 9, and 15. So let's just cross check and see if it's really working. So this particular table over here to my right, this is the truth table for this particular function, because if you notice, the output f is 1 for only the midterms 0, 1, 3, 4, 8, 9, and 15. So let's check the functionality of this circuit by applying these combinations of inputs that I've marked. So this is one, this one, right? So that we see that the function is actually throwing a 1 at its output, this particular arrangement. So here we see CD is 0, 0. So when CD is 0, 0, it is going to choose input 0. So for input 0, it should actually be A dot B, the whole bar, for which we need to know the values of A and B. Here A and B is 0, 0. So 0, 0, the whole bar is nothing but 1. So therefore that's satisfied. There's another 0, 0 combination of CD over here, which we can check, right? These two also. So for 0, 0 CD, again it's going to select A dot B, the whole bar, for which AB is 0, 1. Again, and between 0, 1 is going to be 0. And when we perform a NOT for it, the output is going to be 1. So the same thing is applied over here. In this case, B is 1. In this case, A is 1. So when we do that, we see that for all the three of these combinations, our output is 1. So it's satisfied. Let's move on to the combination where CD is 0, 1. So when it is 0, 1, it is going to choose this. So here the output is merely B dash. So what is the value of B over here? It is 0. So the output it's going to be 1, right? Again, if we look at this, this is also 0, 1. So the output should be B dash. B is again 0 over here. So we'll get an output of 1. And lastly, if we have CD to be 1, 1. So when C and D, both of them are 1, it is going to choose I3. I3 is nothing but the XNOR between A and B. So here A and B, both of them are 1. So if you look at the XNOR truth table, so if I have AB, so XOR is going to be 0, 1, 1, 0. Therefore, XOR bar or XNOR is going to be 1, 0, 0, 1. So for the combination of 1 and 1 for XNOR, the output is actually 1. So we see that for all of these combinations which have been marked for C and D, the output of this multiplexer is observed to be 1. So therefore, we can safely say that this particular circuit arrangement is very well implementing this logical function. So this is the process of using added gates to implement a particular logical function using the multiplexer. I hope this video is useful to you all. To watch more such videos, please to subscribe to this channel. Thanks a lot for watching.